second. So what I want to write down are a couple of extremely fundamental equations that we will be playing with. Okay. So these are going to be Poisson's and Laplace's equations. Okay. So let's just start. So recap. We have two very fundamental equations for the electrostatic field E. Namely, we know the local form of Gauss's law, that the divergence of E is rho, the charge density, over epsilon 0. Again, here I suppress spatial coordinates here because they're implicit as arguments of these functions here. And we also know that, at least in the case of electrostatics, the curl of E is equal to 0. Okay, and here, statics. Okay. So we also know that we can write the electrostatic field as minus the gradient of a scalar. Okay, and here just one little second to say how kind of remarkable this is, how fun this is, because the electrostatic field, of course, it's a vector field. Namely, it has three different values at each point in space. The values of, if you choose three different axes, x, y, z, ex, ey, ez, three numbers. Okay, that's why it's a vector field. However, this vector field originates from a scalar field. The scalar field phi, of course, takes a unique scalar value at each point in space. Okay, so E is a very special field in that sense because of this curlless condition that we have here, the fact that you don't have a perpetuum mobile, it allows you to simplify these things in there. Very important. Yes. Intuitively, it really means that if you I think the best intuitive explanation is really to go back to the force itself, right? Because this is all the same thing in the end, at the end of the day. So the fact that it has no curl really means that if you were to try to create an engine that takes a charge, holds it, and moves it around in cycles, you would never be able to either pump energy into or, more importantly, extract energy by doing that. Okay, so of course later we'll deal with really dynamical stuff, radiation things. So here I'm kind of thinking that I'm in a static field and I'm just moving my charge around. So there's no way to extract work from such an electrostatic field. Okay, there's no way that for free you can just pull out energy of this electrostatic field. The electrostatic field is there and it stays there. It is completely jammed in place by the position of your charges, and you can't do anything with it. It's just there, and it's consistent in the sense that if you move around, you come back, you will always see the same thing. Okay, it's not always going to be the case. Later we'll see when that fails. For now, we're doing statics. That's all I got. Okay. So we have this. Now we kind of see what this relation that it's very advantageous to shift our reasoning to the potential rather than the field, because then we just have one scalar to compute. Also, the integrals for the potential are more friendly than the integrals for the field, because those for the field involve all these vector quantities that we need to compute. Okay, but now you see it took a great historical stroke of genius to put these things together, and therefore, you just plug that representation here in the equations that we have above here, the kind of fundamental equations that we have above. So what do you get? Well, maybe the first one here, the curl of a gradient is mathematically 0 in the first place. Okay, no chance. It's just the way it is. If your vector field is the gradient of a scalar, then its curl is 0. Never get past that. That's the way it is. So actually, the second equation is tautological. as compared to the, once you've told me this, you don't need to tell me that anymore. No content anymore then. However, in the first one, there is content because I'm taking a divergence, and the divergence of a gradient is the Laplacian. Okay, so essentially, if I plug that in Gauss's law, what I get is simply that the Laplacian of this electrostatic potential is equal to minus rho over epsilon 0. Okay, and this is known as Poisson's equation. And then in the online notes, you'll find it really nice because there's a nice little fish symbol associated to it. That's how we refer to it in the notes. So this is Poisson's equation. But Poisson was kind of maybe unsuccessful publicist, unlike his friend Laplace, who said, but let's just simplify for cases when the density vanishes. So when rho is equal to 0 in a certain region in space, you just get this equation. Laplacian of phi is equal to 0. And this is Laplace's equation, which is immensely more famous than Poisson's equation, which is kind of funny. But that's the way it is. Okay, so these are absolutely ultra fundamental, important, crucial, interesting, beautiful, useful, whatever you want to call them, equations. Okay. Yes. Question.
What does it mean when
yeah. So here, yeah. Thanks for that question. Clarifications. So first statement. Once again, I am leaving implicit here the mention of a spatial position, but really what I mean with this equation is that the Laplacian of the field evaluated at a position r in space is equal to minus the density of charge evaluated at that position in space divided by epsilon 0. Okay, that's really what I mean with this. I haven't written the arguments here, but that's what I mean. It is a local equation. The density at a certain point r in space sets the value for the Laplacian of the potential at that point in space. And this equation knows nothing about what occurs at point r plus epsilon, where epsilon is any chosen vector. Okay, it's an ultra local equation. Yes. We will do so much of that. You will be utterly satisfied by the end of your day, I hope. We will discuss a lot. Yeah, because of my next statement, you'll see how important your insight is in here. Okay, so that's the first comment. The Poisson equation is ultra local. Yeah, so local in this case we're doing statics, so there's no locality in time. Everything's not moving, but it's local in space here. So it's really all action is happening at one point in space. Okay.
Action then is at the point charge.
Yeah.
Okay, and infinite is small.
Yeah, exactly. Okay, so and we will discuss the mathematical properties of this in the coming hour and whatnot. You will see how deep we're going to go into that. Okay, so that's the first statement. So the first statement is that this Poisson equation, and therefore also the Laplace equation, is a local equation. Interestingly, you see that indeed the only places where I have to deal with Poisson's equation is if at that place I have charge. That's, of course, that's an interesting stuff, but it's not necessarily typically everything you want to know. What do you typically want to know? You've got charges floating about in your lab, wherever, and you want to know the value of the potential somewhere away from all these charges. Okay? So somehow, the value of your potential somewhere depends on these boundary conditions you give in various places. We'll discuss that a lot. However, most of the fields that you are interested in, all the ones that carry all this interesting physics that you're interested in, they are actually, where you're playing with them, solutions to the Laplace equation. Okay? So electrostatics, in a sense, has been completely transformed into a mathematical problem, namely the classification of all solutions to the Laplace equation. Okay? And we will make statements about the existence, uniqueness, format of these solutions as we progress. Okay? You have also seen the Laplace equation in your first course, if I have it right. However, you probably didn't play very much with it a little bit. Okay, so we will play much more with it than anything. Okay, so that's the first thing. Okay, so once again, you know, that's the way you do things. You know, keep things simple. If you've got something corresponding to Poisson's equation, really complicated and whatnot, you know, don't miss out, right? So Poisson is much less famous than Laplace because Laplace knew how to find the simplification needed here. Okay, so in the second hour, we will discuss this in excruciating detail.